Welcome to another podcast. This episode we're going to be taking a look at the fourth example of the eigenvalue method here, and we've previously done real roots, and then we took a look at two different cases for repeated roots, one where you have a complete eigenvalue and the other where you have defective eigenvalues. And in this video we're going to take a look at the final possible case, which is complex eigenvalues. So if you have a complex eigenvalue, that means the characteristic polynomial has complex roots. And so let's just look at an example of a system. So we're looking at the system with coefficient matrix 1, 2, -1, -1. And this system will have complex roots as long as its characteristic polynomial has complex roots. So the characteristic polynomial here is lambda squared minus the trace. So the sum of the diagonals is 0. And then the determinant is -1 plus 2, so it looks like it is plus 1. So our characteristic polynomial here is lambda squared plus 1, which has roots lambda equal to plus or minus I. So I'm going to focus on the positive root, as has been our custom all throughout the semester when involving complex roots. And so if lambda is equal to I, then I'm looking at the matrix A minus lambda I, so I need to look at A minus I, and then I'm looking for the eigenvector alpha that corresponds to the eigenvalue I. So this would be, so A minus lambda I would be the matrix A with I subtracted from the diagonals. So this would look like 1 minus I, -1, 2, and then -1 minus I. And then let's let alpha have components A1 and A2. And so we've got to solve for A1 and A2 that are going to give us non-trivial solutions here. And I think the easiest way to go about doing this is, and you can see that if I multiply this side, if I multiply, so this is column 1, this is column 2. If I multiply column 1 by 1 minus I, that's equal to column 2. So this is in fact singular. And the question is whether or not, what I should do to solve for A1 and A2. And I think for most students, the easiest way to do this is to write out the equation. So let's look at the first row. The first row would need to satisfy 1 minus I times A1 plus 2 times A2. That would need to be 0. If I solved this for A2, then A2 would be equal to, let's see here, I would have I minus 1 divided by 2, because it would flip it because of the negative. So we would have this relationship between the two of them. And so that implies that if A1 was going to be 2, let's say, we'll make it easy on ourselves, if A1 was 2, then that means that A2 would be I minus 1. And so you can see here how I tried to make it easier by making A1 2 instead of 1 to get things to cancel out nicely. So that's the relationship that they share, and so my complex vector alpha is 2 and I minus 1 are the components. Now, one of the things that you should do is recognize that the vector alpha here is complex, which means that I can express alpha in the form of a vector A plus IB, which I'm going to do now. So the vector alpha is 2 over I minus 1, which the real part of that vector is the 2 and the -1. And the imaginary part of that vector is 0 for the top component, and the bottom component has an imaginary part of 1. And so you can see here that I've decomposed my eigenvector into its real and imaginary parts. So what would my solution be? If this was the case, lambda equal I, then my solution x of t would be this alpha e to the it. So let's form that solution. My complex solution is 2 I minus 1 e to the it, which when I break things up even more, then what I have is the complex vector separated into its real and imaginary parts. And then I know e to the it by Euler's formula is cosine of t plus I times sine of t. And so this is a two-dimensional system. So this is a 2 by 2 matrix. So A is 2 by 2, which means I need two solutions. This is only one solution, and it's complex at that. But if you recall, if I wanted a real solution, then you recall earlier in the semester the way that we handled that is we defined our solution in the real plane to be so this is the complex solution, and I think our custom has been on complex solutions. Well, I'll just leave it in terms of x, but our custom has been to call it z. But x of t is equal to, it would be c1 times, I need to take the real part of the complex solution plus the imaginary part of the complex solution. And these two turn out to be linearly independent. This has been something we've been doing all semester in various forms, and it comes to fruition here as well. So the question is, I'm looking now back at this complex sort of where everything is broken out into its pieces version. This is our complex solution. And I need to recover the real and imaginary parts of that solution. So let's start with the real part. The real part is this vector times this, and it'll also be this one times this, because the i's will give a -1 there. So putting all of that together, we're going to have 2 -1 times cosine of t, and then I'm going to have minus 0,1 sine of t. So that is the real part. This is the real part of our vector x solution. Plus c2, the imaginary part. So the imaginary parts are the things multiplied by i's. You're going to get from here, 0,1 times cosine. You're going to get 0,1 cosine t. And then looking for also multiplied by I, sine times 2 -1. And so there's many different ways that I could go about writing a final answer down for this. I think one of the best ways when you have complex is to just leave it in the vector form that we have here, except to combine the components. And so what I mean by that is we'll call it C1, and then let's do the vector for the first part. The vector for the first part is 2 cosine t. So I'm reading across the top. And on the bottom, it's minus cosine t minus sine t. So the first component there is this vector. And the second component has vector, if I read across the top component is just 2 sine t. And the bottom component is cosine t minus sine t. So I think this is one of the better ways to write the final answer. But either way, either of these two ways is the solution. So this is the imaginary part. So our solution here would look like this. All right, so not a whole lot different than what we did earlier in the semester. You use only one of the complex roots. You don't need to use both, so I usually choose the positive one. And then you go ahead and solve for the complex solution. So this is a complex solution. Once you have that complex solution like we have here, you break it up. You break up the vector into its real and imaginary parts, and you break up the exponential into its real and imaginary parts. And then your overall solution is C1 times the real part of that expression plus C2 times the imaginary part of that expression. And that will be linearly independent. All right, thank you for watching.